Okay, let's take a look at our blackboard. Open the box. Anesthetic foam. There's the blackboard. Going to get it out. Okay, so just a quick orientation. What we've got here is, well, the main chip in the middle of the board. That's the Xilinx chip that we're going to program. When we write Verilog code in the Vivado tool and program the board, it goes into that chip and configures that chip with whatever unique logic circuit we've designed. All the slide switches here and the push buttons here and these push buttons and all of the LEDs are connected to that chip with traces on the circuit board. Can't really see them because they're sometimes inside the middle of the board and they're real small anyway. But this chip has connections on the bottom of it. There's 400 pins, 400 little microscopic pins in the bottom of that chip package that are available to all the external devices. So about 36 or whatever of them go to these external devices to turn on LEDs and to receive switches as inputs. So here's the main power connector, the main USB ports right here. So for the most part, when I use the board, I'm going to plug in my USB cable to that port. And I'm trying to find my USB cable. It's somewhere in my cluttered desk. I'll plug the micro end into this port, and then I'll plug the other end into my computer. It's here somewhere, I'll find it later. And that'll power up my board. Now, I got to make sure that there's a jumper block right here labeled external power, EXTP, and USB, and this little blue plastic thing slides on and off. I want to make sure that's connecting the center pin to USB. What that does is direct the main power from this connector, this USB connector, to the board. If I put that jumper in the other position, that's going to direct the main power input to come from this connector. Now this is another micro USB connector, but no data signals are attached, only power. And the idea is if you need more power, if you're hooking in motors or other high power devices to the board, you can plug in a cell phone charger here, and they typically deliver more power than your computer's USB port does. So that's what that's for. But for the most part, you're going to leave it on USB, so I'll put it back there. And then after you plug it in, turn it on, then you got to make sure to use the on-off switch there to turn it all the way on. Okay, that's most of what I wanted to show you. We'll talk about some other devices on the board a little bit later. So, let me look one more time for my USB cable. And then we will go to the computer. All right, well, you know how to plug in USB cables. I can't find it right now, so I'm going to go find it, and then I'll be right back, and we'll go to the Vivado tool and use the board. Okay, let's go open the Vivado tool. Come down here to the Xilinx tools. I've got a lot of different versions involved. I want to choose the correct one. Most of you probably installed Vivado 2020.1. Don't choose this one. The HLS version is something different. Might talk about that later. You want Vivado 2020.1. So while that's loading up, let's go open our website. And I'm going to look at the first project here, and in particular, the first tutorial in that project. So I'll open that up. Okay, the tool's open. Come back to the Xilinx tool and create a new project. First thing. Now you have to go through a couple of steps when you create a new project to define the environment. Tell the tools what it is you're up to. First of all, I'm going to give it a name. I'll call this, how about EE214 Project 1. And I set up a directory earlier on my C drive. So I'll go select that. What did I call it? Hopefully something meaningful. There we go. 214 project. You can call it whatever you want. Next. I'm going to select an RTL project. RTL is an acronym meaning Registered Transfer Language, and it's kind of an older, maybe even outdated method of referencing text-based designs. More frequently, we'd call it an HDL project, and in particular, we're using Verilog, which is a hardware design language, HDL. The other main language these days is VHDL, but we're going to use Verilog. Anyway, RTL is the correct choice because we're going to use a text-based entry method. Click Next. And I'm going to create a file. Don't have any files to add yet, so I'm going to create one. It's going to be of type Verilog, and here are your choices. I'm going to use Verilog, and I'm going to call this, how about EE214 Project 1 Requirement 1. That way I can figure out what it is later. Okay. So that's going to define that file that I can then type in a little bit later on. Next. Here I can add a constraints file. Now, constraints are commands that you can give to the tool that are kind of outside and maybe even above your design file. So we're going to create a Verilog file here in a second that describes behaviors we want to have in our digital circuit. And that Verilog file can be programmed into the chip on the blackboard. Now when we do that, there are several devices on the blackboard we'd like our circuit to access, things like buttons and switches and LEDs and whatnot. A constraints file provides the mapping between my Verilog source file and those physical devices on the board. When you think about it, I could design any number of circuits and program them into the circuit, into the chip. And I need a method of telling the tools when I define that circuit, which of those circuit names, which of those circuit nodes that I've created, I want to connect to which physical devices. Well, that's what the constraints file does for us. There are also other kinds of constraints. You can have constraints to help locate certain things you'd program inside the chip, or you can kind of set up some timing issues in models, but we're not going to deal with that. For the most part in this class, constraints are going to mean commands that connect external devices to your internal circuit nodes. I'm going to create that later, so I'm just going to click Next here. Now I've got to choose the actual chip that I'm going to use for the design. Xilinx makes dozens, if not hundreds of chips, and they're all listed in this big old table. Well, I got to go find the one that I'm going to use. Back here in the tutorial, here's the part number right here that shows you the part that's on the circuit board. In fact, if you look at the picture here, there's the same part number on the chip, and if you look at the top of the chip in your board, you'll see that same thing. So I need to go find the XC7Z007. That much of it is the chip that we're actually using, the piece of silicon inside the chip carrier. Here in the picture, this is called the chip carrier or the chip package. The chip itself is much smaller than this. It's located inside of this package and then connected to all the bumps in the bottom of the package. But first you got to find the chip, XC7Z007, and then the package the chip is in. This package here you can see in the photograph is called the CLG400 package. And the -1, that's the speed grade. That means when they manufactured this chip, this chip was sorted into the higher speed, faster speed grade. So that's what we want to find back here in this table. Let's see, XC7Z, did I pass it? Yeah, I passed it. XC7Z007 CLG401, there it is. So I'm going to select that one. Next. And that creates our project for us. So it's going to load then the project view. Now on the left here, let's see, define module. I'm not going to do this now. This little box that pops up is a wizard that makes it easy to define input and output signals to and from your design. We'll use this later, probably in the next requirement, but for now, let me just go over here real quick. All we're going to have you do is cut and paste an existing source file into the tools just to get the flow down. But eventually, later on, you're going to have to type all of the input and output signal names. And right here, I've highlighted those in the Verilog source file. The module statement and the input and output statements define all the inputs and outputs from your design. So you're just going to cut and paste them this time, but later on you'll have to define them. And that's what this little wizard does for you. It makes it easy to define the inputs and the outputs. We'll come back to that later. So for the time being, I'm just going to hit cancel because I don't want to do any of this stuff. Are you sure you want to cancel? Yes, I do. Okay, so now here we have the project manager pane on the left, and this kind of shows you all of the options and tasks and sub-applications you have to work on your project. Over here I've got the sources window. This shows me all the source files I'm dealing with. And so far I've only got one source file. I'm going to click into this little guy here. That's the one we just defined. Remember the name, EE214, project one, requirement one, .v stands for .verilog. So that's the source file name. We're going to see all this stuff here a little bit later. I'll just go through it one at a time. For now, I'm going to open this file. I'm going to double click on it, and that's going to open it over here in the editor panel. Now, if you read through the tutorial, what we're telling you is just pretty much cut and paste all the information in this file, in this source code listing, Control C, into this first requirement, Control V. So now this is a complete and done Verilog file. Pretty much for the rest of the class, we're going to learn what to type in here and how to use Verilog to define circuits. We're just giving you one now that's already done, so you don't have to worry about typing the code. You can just see how the tools flow. Again, most of your time later in the class will be spent typing, proper Verilog commands in here. For now, we just gave them to you. All right, so I'm going to save that. Now, once I've got the source code in there, I'll come back down here. Now we have to add design constraints. Now we have to tell the tools which pins, which input and output signals are connected to which devices. If you come back and look over here, I've got some LEDs defined, and this is a 7-segment display. There's some buttons and switches that I guess this first one isn't using. But all these devices, I need to tell it where the physical connections are. So I can come back over here and I can add a new design source. I'm going to click on the design source or the add source thing in the project manager because I want to add a new source. This time I want to add a constraints file. Next. Now I could add files here, or I can create a new file. I'm going to create a new one, and I can give it any name I want as well. I'm going to call this EE214. I'm just going to say P1 for project 1 because I'm going to use the same constraints file for all the requirements in this project. And it'll be automatically linked to all the source files in my project because I'm in the same project here. Okay. And then I'm going to finish because, again, I'm going to cut and paste the contents into that file. So now I can click on the constraints, and again, there's the file I just created. It's called the .xdc file. XDC is Xilinx design constraints, and the .v file here is Verilog. Pretty much all your projects are going to have a .v file to define the circuit behavior, and an XDC file to define how the nets are mapped to physical devices. So I'm going to double click on this and open it up. Now here's a blank XDC file. A little later in the tutorial here, we give you all the constraints. So same thing, I'm going to copy all these guys, select them all, and Control C, come over here, Control V, and paste them in. Now I'll talk more about constraints a little bit later, but we'll just pick on one here. Set property -sign DICT, package pin, and some stuff about what the electronics of the pin are, and then the name of the port. Let me make this a little bit bigger here. So essentially this line here is telling me that a package pin R19, you can see these are all different. These are all different pins. And you can think of the 400 pin package that we're using on the board. You can think of it as kind of a two-dimensional matrix, or maybe like a spreadsheet, where the pins along the left side are given letters, the rows of pins are given letters, A, B, C, D, and so on, and across the top they're given numbers. So it forms a grid with letters on the left and numbers on the right. So pin R19 is in row R, column 19. Again, if you flipped over that chip that's soldered to your board, you'd see a 20 by 20 matrix of pins. And this is how they named them. So this is saying pin R19 on the chip is connected to LED number 2. It's saying down here, let's go somewhere else, pin number J16 is connected to segment 5 of the 7-segment numerical display device on your board, and so on. So it's a pretty straightforward syntax. I'm going to save that as well. All right, now back here in my project, I've got a Verilog file describing circuit behavior, and I've got a constraints file showing how that circuit is connected to the external devices. And that's pretty much all I need for my project. Now I can use the tools to turn those source files into a programming file I can transfer to my Blackboard to make my Blackboard do the behavior I've designed. And these are all the steps that have to happen to do that. I can click them one at a time. For instance, I can click Run Synthesis. I'll go ahead and do that now. It's going to run the synthesizer. And what the synthesizer does is take the Verilog commands and turn them into physical circuits. Now this takes a little while to run, and my only indication is up here in the corner. I don't know if you can see this little spinny thing running in the upper right corner, showing me that the tools are actively doing something. Now as the tool gets a bit further, down here in the console window, I'll start seeing any messages or any logs or reports that are generated. If I put it on log, I can see all the steps that are happening. It'll just kind of spew out the little steps that it's taking. So as it's synthesizing here, it's again analyzing the Verilog code and mapping that Verilog code into the available resources inside the zinc chip, so that the chip behaves according to the Verilog source code. When it finishes, if I want to, the reports tab here will show me reports of how many of the resources were used in the chip and how much time it took and that sort of thing. Okay, so synthesis completed successfully. That's good. Now this dialog box, it's showing me that I can just go ahead and run this step, run implementation. I can do that from here, or I could close it and click over here. Either one's fine. I'll go ahead and run the implementation. Now the synthesis step, I'm going to hit OK, and again this little spinny box up here will start running. The synthesis mapped my Verilog code into the circuit elements available on the chip. The implementation step is now taking the constraints file and mapping the physical constraints into the design so that all my inputs and outputs are hooked up correctly. So I've got to run synthesis and then run implementation. When implementation finishes, the last step is to generate a bitstream. The bitstream is the file that I actually program into the FPGA. So when this finishes, mapping all the constraints into the design, it'll probably bring up a dialog box allowing me to generate a bitstream from within the dialog box, or I could come over here and just click Generate Bitstream again. I'm not sure how long this takes. It's actually doing an awful lot of processing, even for a simple design like this. Okay, now that it's finished implementing, open implemented design. We'll play with that later. That just gives you a graphical view of how the chip was programmed. It's not particularly useful or instructive right now, so I'm going to not do that. I can click Generate Bitstream here, OK, or I could just come over here. I'm gonna hit Cancel in this case. I know the implementation is done, so just for fun, I'm going to do it this way. I'll come down here, click on Generate Bitstream, and why aren't you generating the bitstream? Oh, it is. It's up in the upper right-hand corner here. Running right bitstream, there's that little spinny guy again. So they didn't do a particularly good job of showing you which tools are running at which time. Okay, so now it's producing the bitstream. And when it's done, the next step is to program the Bitstream into the Blackboard. So while this is going, I'm going to plug in my Blackboard and turn it on. And I'll show you this little bit in a video here in a second. That was the Blackboard being plugged in. I don't know if you could hear that. So now we just got to wait for the Bitstream to be generated. Okay, I'm going to cancel again. Well, again, the final step is to open the hardware manager. So I can do it from this little panel, or I could close it and come back over here and click it, same thing. I'll just do it from here. I'll say, okay, open hardware manager. Now the hardware manager is the piece of software that knows how to connect the Vivado tool to your Blackboard. So it's an essential link in the chain. I'm going to hit OK, and it's out there looking to, yeah, thank you, looking to see what hardware is available. So no hardware target is open. I'm going to click Open Target and Auto Connect. I could also do that down here in the menu. And now it's going to go out and look for anything connected to the computer that looks like a Xilinx board, and it should find the Blackboard. Let's see if it does. Yes, it did. What do you know? So now it's connecting everything together. Thought we hung there for a second. And now that it's found the Blackboard, I know you can see right here it's found the right chip in the hardware manager, so that's the right part. Now I can program it. I can click Program Device here, or I can come down here and click Program Device, doesn't matter. I'll click here. Yep, I want to program that device, and it's going to automatically load the bit file we created. So now I can just hit Program. Boink. And it's transferring it to the Blackboard, and now you can't see it, but I can. All the LEDs are on and sort of blinking, and there's a little pattern going on the 7-segment display. So that concludes this first tutorial. I'll make another video here in just a second talking about the second tutorial. Okay, let's do the second tutorial in Project 1. Let me scroll down and open that up. For this tutorial, we want to connect an input slide switch to one of the LEDs. And I think to start with, yeah, the project just calls for directly connecting one of the switches directly to one of the LEDs with nothing in between. So a fairly simple project. But this time, instead of copying and pasting source code, we'll just go ahead and type it. So I'm going to open up Xilinx again, the Vivado tool, and it's still open to the previous project that we did, the first tutorial. So I have a couple of options here. I can create a whole new project, and in fact, here in the tutorial, it's saying go ahead and create a whole new project. And I'll do that, but I want to show you another way you could do it instead first. What I could do is, I didn't mean to make that bigger. What I could do is use this exact same project. So this project, E214 Project 1, is just a directory on disk. In fact, let me just go show that to you. So here's my local C drive here, and here is the directory structure, EE214 projects, and in there I created Project 1. That's what I typed into the Xilinx tools to Vivado, Project 1, when I created this project. So it made this directory for me, and then it populated it with all of the files that it needs. And here's the project descriptor file here. So in Project 1 now, I've done requirement 1. What I can do is eliminate or get rid of this, unlink these source files if I want to, and put new source files in here. I can just click on this and say, remove. I right-clicked on it and said remove file from project. Now that will not delete it from the disk. I guess if I check that box it would. It leaves it exactly where it is. It just unpopulates its reference from within this project. And I could do the same thing here. I could right-click on the XDC file, remove it, it's still on disk, it's just no longer a part of this project. So now if I try to synthesize, there'd be nothing to synthesize. Now from this point, I could go back and add sources again, and I could do the same thing as last time. I could add a new design source into the project, and I could do the tutorial for the second tutorial and type the source code in the same folder. And it would work just fine. Then I could synthesize it and download it as before. And in doing that, if I went to my repository, my disk here, I'd have just one project, but then in the sources file, I'd have more source files. I'd have project 1 requirement 2, project 1 requirement 3, and so on. And that's one organizational scheme you could use. If I do what the project tutorial says, that's fine as well. I'll just end up with more top-level directories here. So I think if it were me, I would just stick with the same project here and have my source files be in one project. But I can always go back and do another requirement. Hope that made sense. Well, for right now, let's go ahead and I'm going to use this project and put the source file in here. But then I'll go back and create another project towards the end just quickly, just to make sure that that makes sense as well. All right, so I'm still inside project 1. I'm going to add myself a new source. And again, I can click on the add sources link here. Or if I want to, I can right click on design sources here and come down and add sources. Either way is the same. So I'm going to create a new design source. So I'm going to say next and create a file. It's going to be Verilog. I'm going to call this one EE214 project 1 requirement 2. Okay. And then that's all I'm going to do here. Now I'm going to go ahead and use this wizard we talked about last time to define my two signals. Now I know that I want an LED output and a switch input. So I'm going to type SW, and that's going to be my switch input. And it's an input here. It's not a bus. A bus is a collection of related signals. I'll talk about buses later. So that's all I have to do. But then I'm going to add another one. I'm going to add LED. Oops, I didn't type in there. LED. And I'm going to make that be an output. And that's all I'm going to do right now. I'm going to hit OK. And then it'll create a source file for me. I'll go ahead and open the source file. Here's what it created. And when I open it, you'll see that it's already, you'll see it's already put those switch, those input and output definitions in there for me. And that's really all that that little wizard does for you. Now, in this area here, between the end of the module statement and the end module statement, so in this area where you're showing the yellow box, that's where I'm going to type my Verilog commands to implement the design that I want to implement. Let me go back to the requirements here. So all we're going to do in this instance is pass the pass the switch signal straight through to the LED. And that just requires this one statement. Assign the output LED. The keyword assign is what we use to assign values to output signals. So I'm going to assign LED the value from switch. I'm going to type that right here, just exactly as shown there. Assign LED equals switch, semicolon. And that's it. That's all I'm going to do in this Verilog source file. So I can save that. Now I need to add a constraint file just like last time. So I'm going to go over to constraints and right click on it and say add sources. I could have also used the project manager setting on the left there. So add sources, add or create constraints, next, create file. And I can call this whatever I want. I'll call this EE214 project 1 requirement 2. Okay. And finish. And now that will add an empty constraints file. Open that directory. There it is. Double click on it. Now last time we cut and paste the constraints from the all the constraints in there, even though we only used a few of them. This time I'm going to go ahead and type it in, but I'm going to cheat and I'm going to go copy this line from the tutorial 2. Control C, Control V. And again, this line is saying that R17, which is the first switch, switch 0, I'm going to assign to switch. Now I need the same line to assign my output LED. So I'm going to copy that and put it right here. And I called my output signal. I'm going to look over here in my source code, next tab over, just to remind myself, I called my output signal LED. My input signal I called switch. And those same exact text strings need to appear in the XDC file. Well, I've got switch already, so I'm going to make that the LED. But now I've got to find which pin number is associated with that LED. There's a couple of ways I can do that. Probably the easiest way is to go back to the Real Digital page here. I'm going to click on the logo and go to the resources page. And in the resources page, there's a GPIO link. I'm going to click on that. That's going to bring up a descriptor showing me, right down here in the middle is a picture of the FPGA. And here's pictures of the slide switches and push buttons and LEDs. So I can see, sure enough, switch 0 is hooked to R17, and LED 0 is hooked to N20. So right here, I'm going to go type N20. And that's it. That's all I need for my constraints file. Let me go back here and go back to where we were. I think we're in tutorial 2. Okay, so now I've got my VHDL, or my Verilog file. I've got my constraints file. Save that. So now I can go ahead and synthesize and implement it. So last time I hit synthesis and synthesized it, and then it brought up a dialog box saying, do you want to implement? Well, the tools use a make file. If I click on run implementation, well, they'll know I haven't synthesized yet, so it'll automatically synthesize first. So I'm going to go ahead and I know I want to implement it, so I'm just going to go click on run implementation. Right there, synthesis is out of date. Okay to launch synthesis first. Yep, let's do that. And so off it goes. And the first thing it's going to do is analyze my files to see if there's been any errors, if I had any syntax errors. And if there are, it'll report them to me and I can go fix them. I'm going to come back here and put the log up so I can kind of watch the processes scroll by as they happen. But if there's no errors, it'll synthesize all the way, and then it'll do the implementation all the way. In fact, I could have clicked on Generate Bitstream, and then it would have done all the processes needed in order to generate the bitstream. So it keeps track of that stuff for you. I guess I'll just sit here and watch with you as we go through the process. Trying to think of what else I can talk about. I guess I could tell a joke, but I'd probably get in trouble. Let's see where we're at. So synthesis completed successfully, it says there in the log. So now it's doing the implementation and it's mapping the circuit to the pins. Should just take a few more seconds. I guess while it's going, I will say that when you run synthesis and implementation, the only files that will be synthesized are the ones shown in the sources pane here. Now remember, I've got EE214 project 1 requirement 1 as a source file still in the directory, but it's not shown in this list, so it's not going to be synthesized. If I added it to this list, I could right-click on design sources and add it to this list, then the tools would synthesize both of those source files because they're both shown here. And for a lot of your projects, you might want to do that. You might want to gang some of the requirements together and put them all in the same project and do them all at the same time. Okay, I'm going to generate the bitstream. There we go. My little spinny guy is spinning in the upper right-hand corner there, so I know the tool's running. And once the bitstream's been generated again, all I need to do is open the hardware manager. I better plug back in my board. I think it's plugged back in, but I didn't hear my little tone. I'm going to assume it's plugged in. We'll see in a minute if it can find the board. Okay, open hardware manager. Okay. No hardware target is open. Open target, auto connect. It's looking for the blackboard now, searching all the USB ports. Yep, it found it. So we're good there. Now I can program the device. I can click up here or I can click down here. They both do the same thing. Program device and program. Now, you don't see my blackboard, but I know it's programmed because there's a green LED right above the 7/7 display, and that green LED turns on when the part's been programmed. And now I'm going to switch one up and down, and sure enough, I'm watching LED 0 go on and off. So it in fact did work. Now while I'm here, before we move on, let me show you something, because I think in the project here, the next part of the project, let's see, modify your code to turn on all the LEDs. Well, I can do that really easily. What I can do is make switch and LED, instead of refer to individual signals, I can make them refer to groups of signals. And to refer to a group of signals, all I have to do is modify the description here a little bit to make it a bus description. Now let me see if I think you can go back and look in the first tutorial here and look at the source code there. Scroll down here, wherever it is. So right here, these statements here, input clock, there's defining a single input. But these statements here are defining groups of inputs that are going to be treated as one entity. So here I can say input, and then I want to have 8, I guess I have a RevD board. There's 11 switches, or 12. I'm going to go with 12. There's 12 switches, so I'm going to follow the syntax in that example. I'm going to say input, square bracket, and then 11 to 0, switch. And that's going to give me 12 signals with the root name SW, but then individual switches will be switch and then parenthesis 0, close parenthesis, switch parenthesis 1, switch parenthesis 2, and so on. So I can get all of them that way. And then for the outputs, I'm going to do the same thing for the LEDs. I'm going to say bracket 11 to 0 LED. Now I've defined, that's all I'm going to change. I've defined now 12 inputs called switch and 12 inputs called LED. Got an extra space there, doesn't really matter. But this statement here can stay exactly the same. This assign statement works on groups of signals as well as individual signals, and it's going to assign LED 0 from switch 0 and LED 1 from switch 1 and so on, all the way up. So now that's complete. That's all I need to do for requirement number 3. Now the other way I could have done it is I could have defined things individually. Instead of doing this, I could have said input, let me just show you, I could have said input switch 0, comma, input switch 1, comma, and so on, and I could have listed them all out, all 12 of them, but that of course is a lot more tedious and more work than just using the one compound statement. So I'm going to go back to where I was. Okay, so that's now legal. Oh, I forgot my comma. Legal Verilog, and I can synthesize that. But could I program it into my board? Well, no. I'm going to save this, but remember in my XDC file now, I've only assigned a single switch and a single LED. Well, there's no shortcuts here. I'm going to have 12 switch statements. And okay, so all I did is I made 12 copies of each of those lines, just jumped ahead a little bit. Now I'm going to go back into the reference manual page, back to resources and the GPIO page, and I'm going to get the pin numbers off here to make sure I don't mess anything up. So switch 0 is R17, switch 1 is U20, switch 2 is R16, switch 3 is N16, switch 4 is R14, switch 5, where to go, is P14, P14, switch, oh, I see one thing I've messed up here. So notice here the document starts at switch 0, switch 1, switch 2, but I started mine at switch 1, and that's an error. I'm going to go back and make this switch 0, because when I use the Verilog method of assigning groups of signals, it automatically starts the count at 0 unless I tell it otherwise. So 2, 3, 4, 5. If you get bored, watch me do this. You can fast forward in the video a little bit. 6, 7, 8, 9, 10, 11. Same thing down here. So what I'm going to do this time is be a little bit smarter. LED 0, and then I'll just get rid of this one. I'm sure you guys were way ahead of me on that. All right, back to here then. What do we got? We got switch 0, R17, then U20, R16, N16, R14, P14, left off right there, L15, then M15, then T10, then T12, then T11, then T14. That's the switches. Then the LEDs are going to be N20. That should be right. It is. Then P20, then R19, then T20, then T19, then U13, then V20, then W20, then W19, and then Y19, and I'm out of LEDs. But if you look in this picture here, you can see that the RGB LEDs actually are just individual LEDs. So I can just turn on a couple of these with the switches as well. So I'm gonna hook, I guess, to the red LED. I'll hook this one to W18. So that's going to drive that LED, and then Y14. Okay, so that's my completed UCF file. I'm going to save that and go back and check to make sure everything looks right. Well, that's pretty simple. That looks right. Got all the right pins in there. Okay, so I'm going to go ahead and this time I'm going to click on Generate Bitstream and let it run through the whole shooting match itself. Since this is out of date, yep, do all that stuff. So I'm going to start that. I'm going to pause the recording, and I'll be back when the process is finished. Okay. Okay, so the Bitstream was written, and I'm going to cancel out of that, and then we're going to open our hardware manager and program the device. I think it's already open. Yes. So open target. Sorry, and program device. There we go. And making sure it's got P1R2, and it does, so we got the right bitstream, and program. And I'm watching the board program, and what I'm looking at now is my working design. So every time I move a switch up, an LED turns on, and the last two switches turn on the red LEDs as intended. Okay, so that was requirement 3. Now let me go back and show you just quickly what we could have done instead of all this. We could have gone up here as the project tutorial mentioned. If we go back to tutorial 2 here, it said here to create a new project. So we could have done that instead. And to create a new project from here, all I would do is go to File, Project, New. And then I'm right back where I started at the first tutorial. Next, I can give it a name. I could call it Project, maybe I'll call it Project 1 Part 2 or something like that. And go through the same flow, RTL, create file, just like we did before. So either way, your choice. Okay, that's it for this one, and I will talk to you guys again at the next class period. Good luck.